In this video, we're going to take a look at finding the domain from functions. Basically, we're going to be asking ourselves the question, what can x be? Two types of functions we're going to focus on are square root functions and rational functions. What I want you to notice is really when we're working with square root functions, whatever is underneath the square root or the radical is really all we're concerned with. So we're going to focus on that, take whatever is underneath there and make it greater than or equal to 0 and solve it. And that will be our domain. For rational functions, very similar. The one thing we can't do is we cannot divide by 0. So we will take whatever's underneath the division bar and we'll make that not equal to 0 and we will solve for what x can be or really what x can't be. Now typically when we're solving domain problems, we're thinking everything is all real numbers. Unless there's an issue like square rooting a negative or dividing by 0. And those are the two cases we're looking at. These are just different ways we look at writing all real numbers. Sometimes you see the fancy R, x is an element of R. X is your answer such that x is an element of all real numbers. But mostly people like the interval notation of negative infinity to infinity. So something that will always be all real numbers are all your different polynomials. They'll just go on forever, whatever that polynomial may be, from negative infinity to infinity. You might see it with x squared, so quadratic equations or linear equations. Let's get into our 7 examples. Our first example is just looking at a radical. So let's take a look at what's underneath the radical, 4x plus 3, and we're just going to take that 4x plus 3 and make it greater than or equal to 0 and solve it. Again, we're just solving for domain. So we'll subtract 3 from both sides, leaving us with 4x is greater than or equal to negative 3. We'll divide by 4, and we're left with x is greater than or equal to negative 3/4. Now, on a number line, we would look straight across, and we'd be thinking negative infinity to infinity, with our value at negative 3/4, and we could be from negative 3/4 all the way up to infinity. So in interval notation, we would write negative 3/4 inclusive, so it's a bracket, comma, to infinity. And we can never reach infinity, so that's our answer. Our next example, very similar, square root function. We don't care about this plus 2 out here. We don't care. We just care about what's underneath that radical. So that 5 minus x. So we're just going to take 5 minus x and make that greater than or equal to 0. Simple strategy. Most people would subtract 5 first, so let's go ahead and do that. And then they would divide both sides by negative 1. This is just where you need to remember, if you divide by a negative, you need to flip the inequality sign. So we're left with x is less than or equal to 5. Again, we can throw it on a number line, just so we can see it if we need interval notation. So we're going to put our key points, the 5, negative infinity to infinity. So we can be 5 or less than or equal to. So now our answer in interval notation is negative infinity to 5, and the 5 is inclusive again. Example 3 has us looking at a rational function, or some people just call them fractions. We're just concerned with what's in the denominator because we cannot divide by 0. So we're just going to take x plus 4 and say that cannot equal 0. So we're really just asking ourselves, what would make it 0? So we're just going to go and solve this like we normally would any equation, even though it's an inequation. X is not equal to negative 4. This is a little tricky for some people in terms of interval notation, so let's go ahead and put it on a number line. Negative infinity to infinity. We're going to mark off negative 4. Now it can't be negative 4, so that's an open circle, but we can be all the numbers to the right and all the numbers to the left. So really we have two pieces here. We're going to go from negative infinity to negative 4 non-inclusive, union with, which just means or. And again, we're going to pick up right after negative 4 and go up to infinity. Example 4 looks a little more complicated. It is. But again, we're only concerned with what's in the denominator. And what we have is a quadratic. So we're concerned with what will make this equal to 0. So I'm going to go ahead and write down x squared minus 2x minus 15 is not equal to 0. Since it's a quadratic, we're going to go ahead and factor that. And if you forgot how to factor, you can go ahead and take a look at some of my videos on factoring. So we know it's x and x multiplies to make negative 15, adds to make negative 2. So we're going to have minus 5 plus 3. And then we're going to take each piece here and say neither of those can make 0. We don't want that to happen. And so what would make that happen would be positive 5 and negative 3. So it can't be 5 and it can't be negative 3. Again, interval notation, a little tricky here. Let's set this up. We're going to have negative infinity. Next smallest number is negative 3, and then 5, and to infinity. So it can't be either of those, but it can be every other number. So we can fill that in. So now we have 3 pieces. So we're simply going to have negative infinity to negative 3, non-inclusive, union with, and then the piece in between, a lot of people leave that out, negative 3 to 5, union with that last piece, 5 to infinity. Moving on to our 5th example, you're going to notice 2 things. We have a radical and a fraction. When you have this, we simply know that the whole thing can't be 0. So rather than taking what's inside of here and saying x minus 3 is greater than or equal to 0, it's just greater than 0 because we can't make it equal to. So a very simple switch. Solve that, x is greater than 3. Again, this one is much easier. Negative infinity to infinity, we have 3. Open circle to infinity, so we're simply going to go from 3 to infinity. Number 6, kind of a trick question here. Again, we're just concerned with that denominator. We know that x squared plus 4 cannot equal 0. Now here's the great thing on this one. When you square a number, it's not going to give you a negative answer, and if you add 4, it's always going to be positive. So if we do try to solve this, and we try to square a root, we're dealing with imaginary numbers, which that's not part of this. So there's no real number where this would happen. So if this would never happen, we can just say the answer is negative infinity to infinity. And our last one, it's got a little asterisk, it's a little tougher. It's got a couple of things going on, so we're going to do them both. We have an x minus 5 in our radical sign, so we have x minus 5. That has to be greater than or equal to 0. We also know that we have 12 minus x in a radical, so that also has to be greater than or equal to 0. So we have 2 conditions. This 2x, it doesn't matter. So we have x is greater than or equal to 5 when we solve that. When we solve this, we're going to have negative x is greater than or equal to negative 12. Remember, we're going to divide by a negative, so we have to flip that sign. So we have 2 conditions. And if you can't picture this, what will you do? Draw a number line. So we have negative infinity, we've got 5, we've got 12, and we've got infinity. We have to satisfy both conditions. So when we have 5 to infinity, and then 12 goes down to negative infinity, we just look where they overlap, which is from 5 to 12, and we can include them both. And that's it, folks.